and welcome back to Research Methodologies. The topic of today is validation and verification. For some of you this may be a topic you're well conversed with, for others this is a completely new topic. So let's start straight away with the definitions. An easy definition to distinguish the difference between validation and verification is very simple in terms of looking at what it is that you're doing. So in validation, you are checking if you're building the right thing, and in verification, you are checking if you're actually building it the right way. So there's a difference between the two. One, you're actually looking at, is what I am doing the right thing to do? And verification, you're more looking at the process of how am I doing it? Am I doing it according to the existing rules of what I'm doing? So, in other words, validation is actually proving that your outcomes are true and based on strong scientific evidence, and verification is proving that your method of research that you've used have been used in the way they're supposed to do. Like an example, using non-normally distributed data in a t-test is really not on unless you meet certain requirements, and that the methods you're using are also suitable for your research topic. So those are the things that you have to prove, and the stronger you prove, as always, the better the quality of your work. So why is it then needed? Well, the very simple thing is, it is needed to add credibility to your results and to your conclusions, and it allows your results to be used in a professional environment, and very other important thing, it allows you to have academic reproducibility and transparency. Basically, it makes it much easier for people to check if your outcomes are true. It makes it much easier to check if your outcomes are have been done according to the way that they're supposed to have been created, and basically it makes it's like an extra form of quality control that you've carried out on your own process, and basically it should be good working practice that you are able to explain why you've done the things you've done, and why you've used those methods, and that you've applied them correctly, because that basically adds to your credibility and the quality of your work. So where does it all fit in? Well, basically validation and verification completes your research cycle. So if you look at the top, you start here at the observation and formation of the topic, where you start looking in literature, what is already known, which gap is there left, and what and how much of that gap can I bridge in my research, what are the research questions that go with that, and eventually, of course, your hypothesis, the strongest form of a research question, I would almost argue, where in which you've defined your variables and there's a certain question you would like an answer to, ideally a yes or a no, or maybe a little bit more extensive than that. And then from that you go into your conceptual design and your operational design, in which you agree what you're going to do and how you're going to do this. And then the process starts, the data gathering, then you have your data analysis, whatever you do. It doesn't matter if you're doing it behind a computer or in a lab. And then the most important part, the data interpretation. So then you've got your thing, and then you think, oh, I'm done. I just write this all up, my conclusions. And this is the chapter that most people miss out, and this is the chapter where you really, and the part of your research that's really vital that you spend time on, is when you start looking at the validation and the verification. In validation is that you go back and check, did I actually look right at my hypothesis? Was my hypothesis actually formulated correctly, or do I need to do this again? Did I do everything right? Did I answer the question that I set out to answer? And then in verification, you check again if you've used all your methods appropriately, if everything you've done was the way it was supposed to have been done. By the book sounds a bit cheesy here, but more or less that is what we're looking for. Have you applied the right methods to the right data, the right simulation methods, all those things, the codes that you've used, is everything beyond reproach, and how strong is the quality of your work in that shape, in that respect. So if you can prove that you've looked at the validation, you looked at the verification, and that goes beyond the sentence that I've looked and it's okay, but actually checklist type, like I've done this with this method, those are the limitations, and all that worked, etc. And also where it didn't work, because where it didn't work also adds to that. In your verification process, if you said, well, I couldn't do a certain test because the data wasn't good enough quality to do that test, that leaves you room to start speculating, for instance, in your recommendations, on what other tests could be carried out for the next person. So it also shows that you have a very good comprehension of the limitations of your work. And then you may need to revise your hypothesis, and sometimes means you can go into reiteration, that depends where in the process you are, or you go to the conclusions and you put in the recommendations, like some of my work didn't work out and it needs to be redone there and there and there and this, and that can be redone by another person because it involves, for instance, a whole new set of data generation or a whole new development of code. So in that sense, this chapter really is like the icing on your cake. It is where you really show that you rise above your material and that you have a good comprehension of what you do and why you've done it, and you are able to critically reflect on your own work. That is an attitude that's becoming more and more important for engineers to have if we go into industry, or even if you don't go into industry, because problems are getting more complicated, and as the problems are getting more complicated, it is even more important to ensure that there is good validation and verification, because we can't always check the results in other ways anymore. So how does industry do this? Well, if you look at industry verification and validation, you actually see that verification is like a quality control process. It's used to evaluate, to see if a product or whatever it is that they make, a service, a system, it actually complies with regulations, specifications, and conditions imposed at the start of a development phase. For instance, certain original equipment manufacturers, such as Airbus and Boeing, have specifications on the staff that are allowed to work on processes. They have to have certain training. All these other things, do you meet airworthiness regulations, all these things in the verification process. Verification can happen at any stage. It's not something you just do at the end as a little close of the loop. If you're actually clever in industry, especially in large projects, you want to verify consistently all along, because otherwise, if you wait for verification till the very end, you might have had a fully built aircraft which you then can't use. And considering the expenses involved with that, that is usually the end of business for such a company. So verification really should happen at every stage. It can be in any development, scale, in production. And the most important thing is it's often an internal process. It's to see, have we done what we said we do before we send the project out to the customer. Validation is more a quality assurance process, so not control, but more an assurance process. And that is that you actually have an agreed ways of working, and you establish evidence that if we follow this way of working, that a project will actually do what we said it would do. So this means that you talk to your stakeholders and say, look, are you happy if we're going to build this? Are you going to buy this to a certain extent? Is this what you want us to do? It's where you validate in every stage of the process what it is that you're doing, and that it is what the customers want, that it is what the end goal is, that you don't deviate. It's very easy to come off path to do so. It's also something that happened to you in your thesis. I mean, it's very easy. You find all these other things which are also very interesting to do, and we've hopefully raised you, to use a word, as a curious people. So you'll find lots of things interesting to research. But for you, validation is one of the ways to keep yourself on track in your process, to say, oh, is this what I'm doing? And the difference with validation is often an external process, in the sense is that you talk to others consistently to check. So for your thesis, that will be, for instance, your thesis supervisor. So when it comes to industry validation, what do they actually test? Well, they look at selectivity, specificity. Is it the right thing? Is it accurate enough? Think of production. It would be very useful if parts actually fitted into each other. I think of a Lego brick. The accuracy of a Lego brick production is enormous, because every brick must fit onto the next brick with a certain level of accuracy, and must be able to be removed from that brick with a certain specification of force and all these other things. Then the other thing is, there's a precision there and a repeatability, because every Lego brick has to be the same to that extent. And a reproducibility. We're going to do this over and over and over again. We also look at things like limit of detection. If you look at trace elements, for instance, at what point can we detect stuff? What is the limit of quantification? How much of these things? We can look at curve fitting. We can look at system suitability. There are so many different things that every industry looks at, and it's important that people realize that for each of those, processes must be in place. So what are these processes? Well, if you look at systems engineering, you see it in there too. So in there, if you look at it, it's like a V, and you start at the top with the system level design requirements, and that's where you start. You have your design requirements, and then you have a functional review in which you validate, usually with your stakeholders, is this what we're setting out to design at the start? And then you go to the preliminary design review, and you get the item level design requirements, and again you check, are we still on the right path? Are we still designing what we think we're designing, and do we have to reiterate, and all these things. Then a critical design review, which is basically the design review before we press the button, let's go build, and make the real investment. So it's a really important one. Again, you validate with your stakeholders that everything's there. And then you go into the fabrication, integration, and testing side, so you start producing stuff. So you have the components are built, it's assembled, and then you have the technical readiness review, which is a very tense review to a certain extent. Does it work? Okay, so the paper said it worked, now we've built it, does it work? It's like, imagine sitting in a car that you just built and you start the engine and you go, oh yeah, we're getting somewhere. Then you look at much higher level configuration level, subsystems level, to the system verification review, which is basically to the point of, are we now ready to send it out? In the system verification review, you've tested everything, you've gone through every check, you're very happy that everything works the way it works, and at the end of the system level verification review, we are ready to roll, we are ready to sell it to the customer. So that means, so at the bottom of the V, all the design requirements are complete, and then at the top of the V on the other end, you've actually delivered something to the customer. That is basically the way these things work. And if you can do this to a certain level also for your thesis, you make your evidence much stronger. So in a design verification test, which is what often happens, this is one for a telescope, is basically what you do is you do an intensive testing program, because you really need to verify that all the product specifications and interface standards and original equipment manufacturer requirements, etc. have been met. Everything is there. Just imagine a telescope that goes up into space. It is woefully expensive to have it repaired. Ask anybody who had to work with the Hubble telescope. So you have to do it right, meaning you have to validate and verify at every point along the way. So what are areas in which design verification testing takes place? It's functional testing, but also the performance. Does it perform in the right climate? Is it reliable? Will it keep working? Environmental tests, and that is not just pollution, but also the environment in which it has to operate. There's a difference if you build something on Earth and you have to operate it in space. Mechanical test, does it work? The MTBF prediction, the compliance and regulation testing, etc., etc., etc. All sorts of areas that you need to look in for design verification testing. Now, for most standard, for as far as there's anything standard in engineering, but there are lists that you have to go through. But if you're building something completely new, you're going to have to design your own verification tests and convince regulative authorities and your financial investors and etc. that you can do this. So there's a whole process involved with all these things. You have many different ways of doing it. This is a Six Sigma validation example where they look at risk assessment, they look at if something's mistake proof, if it stands up all the different challenges. You look at the measurable outputs and you validate that your measured system works. That's another important thing, is are you actually measuring that what you say you're measuring? What are the key inputs? How are you going to control them? What are your worst case conditions? And then you perform some worst case testing. And you look at what is it coming out, etc. So what you see is basically that in Six Sigma they divide it into three. You have an installation qualification, an operational qualification, and a performance qualification. So the installation is how does it actually work. The operation is when we put the machines in place. The operational qualification is what's coming out when we work with it. And then the performance qualification is does it do what we said it would do. So you have to look at all these different things. Eurocontrol also started their own validation process, and they've actually written a whole document about it. You get the sources on the website, and these are some of the figures from it. So they really wanted to start looking at validation and how are they going to do these, and you can see the time release and how it worked and that they've released the project. And even for these large organizations, these type of documents are vital in how they do their business. So here you see, for instance, that they start looking at the air traffic management needs, when the divisions were made, how they're going to say the process, what they're going to do in which phase of their validation, what parts are happening concurrently, what parts will be happening consecutively. So you can really see where all the different things come in and how this goes. And you can also see that to a certain extent the process doesn't just stop with integrating in it. At some point that it might be the scope of your specific validation. But you can see, for instance, in this project that they've even looked as far as decommissioning. So those are things you can also think of and look at. It doesn't just stop there. So when we look at all these different things, you have to realize that validation is very much a interdisciplinary activity, because you have to look at the business case of it, the safety case in this case, the human factors case, the environment case, the standard case, but also the regulatory case. But a lot of these things do not run consecutively. They run concurrently. They are intertwined. You have to constantly make sure that you have every stakeholder for these things involved in the process. So it's not this is my little bit and my little island, and if I'm fine on my little island, then I have validated my thing, because your validation might be okay, but somebody else might have a big cross somewhere, and that still means that the whole process won't move forward. Whereas if you both sat together and looked at it going, well, if you do a bit more of this and I do, that gives me more room for that, then you both get validation, and then your whole project goes forward. Because in the end, in industry, nobody cares if your shit is in order, it's whether what's best for the business that is in order. And if that meant that you left one of your colleagues hanging out to dry when you could have sorted it out, then that doesn't reflect well on you. So in that sense, these are important things to realize, that it's an interdisciplinary activity. So how does all this relate to your thesis? Well, I've said it before, it's very important that you carry out validation and verification of your thesis. It basically means that you sort of bring your thesis to this level that you basically prove that you are above your work, that you can look at your work and look at it critically. Which is a hard thing to do, because for months you've been looking this close at it, and now you really want to make sure you have less work to do. So, so you have to take a step back to a certain extent, plan it in such a way that you take a step back first before you start looking at it. So one of the things you want to look at is, when you formalize your research hypothesis, which of course you should be very careful in doing this, is it a valid formulation? Was it a good one? And if so, did I maybe need to adjust things? When I set up a research goal, is it actually something that I can validate and prove to be true? Right, if your research goal is to prove that Martians exist, good luck to prove that. Actually, this is why you need to have the by in the formulation. I'm going to prove that Martians exist by, well, good luck with that. So make sure when you start designing your research, which is the phase you should be in now, is that you actually look at validation from the start. Yeah. So the worst thing you can do is just go, well, I'll just do all this. Oh, validation. Oh, yeah. Well, actually, I can't validate that what I'm saying is true. Oops. So yeah, you can solve that by not having a validation chapter in your thesis, and hope nobody notices, but you know as well as I do that that's not going to fly anymore. The same with your hypothesis. Can you make a hypothesis that has a formulation that is valid and that you can actually look at in the terms of your research? And so that actually brings me to the point of, what is the quality of the validation in your thesis research? You have a choice to say how high you want that to be. And actually designing a validation framework for your thesis to have an idea of, this is how I'm going to check there, and there, with these and these cases. For instance, if you're doing software, there's very often a base case where we know the answers, so you can run that as a validation. There's so many different things you can do. Think about that. So And words of Shakespeare, right? To be or not to be, that's the question in our case, to validate or not to validate. And I would really argue that validation would be a much, much better thing to do. So when you design your master thesis, this is basically a checklist. Is there a clear hypothesis? Is there a way to test it without any doubt? Repeatability, reproducibility, all those things. When you design your test, keep an eye out on your timescales, your data acquisition, the quality of your analysis, and what the sensitivities are. And sensitivities can be anything from computational sensitivities, but also measurement sensitivities. Do not just validate the overall outcome in the end, but validate every subcomponent in between. It saves you having to go back after months of work because you find out you didn't do it right somewhere in the start. It's also not a last minute job. 2 weeks at the end or even the last month is possibly not enough. It's much more important that you proactively do this from the start and have procedures in place that you make yourself adhere to. Because that means that when we come to the final exam, in your oral exam, you'll be able to argue why you were right and why it can be proven and why it can be trusted and why it's relevant, and really impress your committee about the grasp you have of the material and the grasp you have of the subject you've been studying. So does not just go for your thesis, no, in fact it goes for all science. So if you look to a certain extent that the ultimate proof of proper validation is if you get to publish a journal paper, and that actually goes not just for you guys as master students, but also for us as staff. I mean, if you have a relevant journal paper, then there has been a form of validation and verification. If you look at rejections from academic journals, so about 75% get rejected. About 75% of the rejections are due to either insignificant impact or poor validation. So insignificant impact would be, well, you haven't really added anything new. We already knew that. You just proved it slightly different, and we really don't see the extra bonus of it. Or it's great that you say that, but we have no idea if it's actually true because you haven't convinced us beyond a reasonable doubt. So the way a journal works is that we have peer review. Other academics in the world volunteer their time to review others' work scientifically. And only the better work, or the work that is proven to, that they feel is proven to be true, gets ready for published. So that's the verification process that's in place in terms of science. So this is often done anonymously, so there should really be no collusion of friends and stuff like that. That still doesn't mean that mistakes don't get made, but it is exactly what happens there. And most of the time, a journal article gets reviewed, when it gets reviewed, it's like, well, you haven't actually validated your results by benchmarking it to something else or proving it beyond reasonable doubt. So, really, if you look at academia as the pursuit and development of new knowledge, your thesis work is going to be original if you can validate it and have it published. I mean, that's more or less the proof of the pudding. However, getting a journal paper published is not always as fast as you'd like. Sometimes that can take up to half a year or a year. So if you do manage to get it published, or your supervisor suggests you get it published, be aware that this is the criteria you want to work towards. So if you get a journal publication, the way we look at it, it's like the ultimate success of your project, because you've proved that not only do we as your supervisors, who you could argue are slightly biased, think it's really good, but the people in the field that you were working in, other independent people, also think it's really good, and they don't know that you're a student because it usually doesn't say this was work as a master student. And why is this all important? Well, it's the same if you do work for industry. They want to have confidence in the reliability of the results. They would like their universities to produce knowledge and innovative ideas and tools that they can use, and they want to have faith in. Otherwise, they will argue, why are we paying taxes to governments for you guys to fund universities? Or if you're privately funded universities, why are you paying all that money? So eventually, if you look at it from a value engineering point, we are creating value here. So the industrial application of what it is that you're doing will create value, and eventually, in a more holistic form of view, it hopefully will improve at some point the societal quality of life that we're looking for. So hopefully validation and verification and why you need to do it and how you need to do it and specifically how you need to implement it into your thesis design process has now been clear. In the next section we'll talk a little bit more about reliability and logic, but for now, good luck with designing your thesis project. Bye for now.